2n square plus, if I write 4n plus 3n plus 6, from the first two terms, if I take 2n common out, I am left with n plus 2. From the second two terms, the last two terms, where I take 3 common out, I have n plus 2. So it's the factorization method that you have already come across in school. Then you take n plus 2 common out. Then you have 2n plus 3. Now this was the sum of the squares of first n plus 1 positive integers. Okay, we have to recognize this as the right hand side when we have n plus 1 in place of n. So if I rewrite this expression like this, n plus 1 plus 1, 2 into n plus 1 plus 1, is it equal to this? N plus 1 was already there. N plus 1 plus 1 means n plus 2, and 2 times n plus 1 plus 1 means 2n plus 3. So we see that our formula is also true when we have n plus 1 in place of n, and that's what we were supposed to show, and this ends the induction. So then you write, hence by induction this is true for all n greater than or equal to 1. So you see that the basis is rather easy. You just have to put some values, namely the first one n equal to 1, and see that the formula is true. Then the induction hypothesis has to be assumed. Then based on that assumption you carry out the induction step, the next step, that is, you have assumed that you can take n steps and then you take the next step, n plus 1 step. You show that that is true, and hence by induction every step can be taken, or in other words the solution is over. Okay, let us take one more problem like this. Show that this is true for all positive integers. 2 times 3, yeah, plus 1 by 3 times 4 plus 1 by n times n plus 1. This is not 1.2, 2.3, okay. These are products, multiplication of two numbers, just like what we have here. And this has to be shown equal to n divided by n plus 1. So same, you apply induction. When n is equal to 1, what do we have? We have only one term, which is nothing but this. And you can see that 1 divided by 1 times 2 is equal to 1 by 2, which is nothing but 1 by 1 plus 1. So the formula is true when we have n equal to 1. This is the left hand side, this is the right hand side, and they are equal. So this is the basis for our induction. Then as induction hypothesis we assume this for some n greater than or equal to 1. We then go one step more. Plus 1 by n times n plus 1 plus, in place of n we now have n plus 1, so this will become n plus 2. So by now you have seen, you can see that it's following the same pattern. Okay, you use this formula here, n plus 1 times n plus 2. N plus 2, so this will becomes n times n plus 2 plus 1. So what does it give me? N square, yeah, n square plus 2n plus 1. This is n plus 1 whole square divided by n plus 1 times n plus 2, which is nothing but n plus 1 divided by n plus 2, or so you can see that the formula remains true when we have n plus 1 in place of n. So we have carried out the induction step and the solution is over. So you can see that what seems like a rather complicated thing to apply mathematical induction is actually pretty easy once you get the point and once you know what to do. Now that we have seen some identities proved using mathematical induction, let us now prove something else using mathematical induction, which is not identity, it is something else. Prove that 2 to the power n is greater than n for all n greater than or equal to 1. We have to show that when we take this power 2 to the power n, where n is a positive integer, it's always greater than n. Here also we will have a basis, an induction hypothesis, and we will carry out the induction step. So for basis, what do we do? In this case, left hand side and right hand side, they should not be shown equal because the statement itself is inequality. We have to show that this is true when n is equal to 1. 2 to the power 1 is 2, which is greater than 1. So clearly for n equal to 1, the inequality is true. Then assume that the inequality is true for some n greater than or equal to 1. Don't forget to write this for some, okay? Not for all. For all we have to show, and we are showing that. We then try to show this, okay? We have to show this. So we start from 2 to the power n plus 1. How can we write this? We can write this as 2 times 2 to the power n, okay? 2 times 2 to the power n. But 2 to the power n is already greater than n. So 2 times 2 to the power n will be greater than 2 times n. Okay, we have used the inequality here to conclude this, which is equal to n plus n. And we know that n plus n is greater than n. Why? Because n is greater than 0. Or no, that's not what I need. N plus n is greater than n plus 1, or greater than or equal to n plus 1, since n is greater than or equal to 1. Add n on both sides, you get this. Okay, so hence, you see, in a chain of inequalities, once you get strict inequality, that one persists, okay, that one stays. 2 to the power n plus 1 is strictly greater than n plus 1. This is what we have to show, and this is our induction step, and we have proved the statement using induction. This is now true for all n. Okay. We can, in fact, using induction, prove this rather familiar result of the sum of a number of terms in a geometric series. If you are familiar with this series, ar to the power n minus 1 is equal to a times r to the power n minus 1 divided by r minus 1, where n is any positive integer, or let me be more specific, n is any positive integer a and b, or sorry, a and r are real numbers and r is not equal to 1. We need this condition to make sure that the denominator here is non-zero. Okay, that always should be the concern. Whenever we have something in the denominator, it should be non-zero. Okay, zero denominator is not allowed, at least at this stage. There will be some situation where zero denominator will be allowed. Okay, but that is far ahead of us. Okay, at one point we will reach that place, hopefully. Now, this is called a geometric series. And a geometric series, as you may already know, is a series which maintains a common ratio between its consecutive terms. If you divide this by this, you get r. Or rather, if you have one term of the geometric series, then the next term can be obtained by multiplying that term by a constant r. You multiply a by r, you get ar. Multiply this by r, you get ar square, and so on. Why I did not define it like this, or a is equal to ar square divided by ar, it's because I don't really know whether a is 0 or not. A may be 0 also. Then this type of definition of a geometric series will make no sense because I am dividing by 0. Okay, so how many terms are there in this series? You see, when we have 1 here, we have 2 terms. So the exponent that is here, we have one term more than the exponent. Here the exponent is n minus 1, so here we have n terms, n minus 1 plus 1. We have to prove this. Okay, technique is same. You first show that the result is true for n equal to 1. For n equal to 1, how many terms are there in this expression on the left hand side? One term, which is a. This is the left hand side. On the right hand side, if you put n equal to 1, you get a times r minus 1 divided by r minus 1, which is also a. So at least in the case when n is equal to 1, the formula is true. Then you assume that the formula is true for some n, same for some positive integer n. Then you proceed to show that it is also true for n plus 1. So you write the sum for n plus 1 terms. The next term will be obtained by multiplying this one by r, that is a times r to the power n. Now this is equal to same. For this part you apply what we have already assumed, r power n minus 1 divided by r minus 1 plus a r to the power n. Okay, so now we do a little algebra. Minus a plus a r to the power n times r minus 1. So this is equal to a r to the power n minus a plus, if we multiply out, a r to the power n plus 1 minus a r to the power n divided by r minus 1. So these two terms cancel out. and we are left with these two. From them we can take a common out. So we are left with r to the power n plus 1 minus 1 divided by r minus 1, and this is precisely this formula when we have n plus 1 in place of n. So this completes our induction step and the solution or the proof. Okay. Now to just simply for the sake of variety, let us also prove something else using induction, which is neither equality nor inequality, but something else, divisibility. This concept will be studied at length and in detail when we come across number theory. Okay, at one point we will study number theory. There we will see divisibility, although we already know what divisibility is. 6 is divisible by 2. This is a statement that you already know from your elementary school. 6 is not divisible by 4. Now, what do we mean when we say that 6 is divisible by 2? By this we mean that 6 can be written as 2 times 3, where 3 is an integer. Okay, 3 is a positive integer. However, if you write 6 as 4 times something, that something of course is 6 by 4. 4 times, you can simplify it as 3 by 2, or it becomes 4 times 1.5. Now this 1.5 is not an integer, it's a fraction. It's a rational number which is not an integer. So that's why 6 is not divisible by 4 and 6 is divisible by 2. These concepts are well known. Now there is a symbol in number theory to denote this fact. Instead of writing this, we write a symbol like this. 2 a vertical bar, then 6. It means 2 divides 6. That is, or in other words, 6 is divisible by 2. In the same vein, 4 does not divide 6, or 6 is not divisible by 4, is denoted like this. You strike this one out. Okay, it means 4 does not divide 6. So with this elementary concept of divisibility, we now want to prove something about divisibility that requires induction. Okay, that is also a statement that requires induction because it involves positive integers. So as an first off, we take an easy one. Show 3 divides n times n plus 1 times n plus 5 for all positive integers n. Okay, suppose we want to show this. Again, using induction. So the method is same. We have to first check the result for n equal to 1. So when n is equal to 1, what is this expression? Now remember, here there is no left hand side or right hand side. This is just a statement. Okay, this is not an equation. This is neither an equation nor an inequality. This is just a mathematical statement that you have to show is true for all positive integers n. So we want to first of all show that it's true for n equal to 1. So when n is equal to 1, what is n times n plus 1 times n plus 5? It becomes 1 times 2 times 6. So it is 12. And clearly 3 divides 12, because 12 is 3 times 4. 6, yeah, 12. So for n equal to 1, this statement is true. Now we assume that for some n it is true. That is 3 divides n times n plus 1 times n plus 5 for some positive integer n. Okay, now we can write this, we can actually express this by writing n times n plus 1 times n plus 5 is equal to 3k for some positive integer k. It's like writing this statement like this: 12 is equal to 3 times 4. Now since here we don't know what this k is, so we have just simply assumed, but there is a k, and that's what this statement means. There is a positive integer k for which this is true. Now we are not interested in this. We want to show that something else is divisible by 3. What is that? The expression when we have n plus 1 in place of n. So n plus 1 times n plus 1 plus 1 times n plus 1 plus 5. We have to show that this is also divisible by 3. So let us try to simplify the situation. N plus 1, then we have n plus 2, and we have n plus 6. Okay, now how can we simplify the situation? You see, this is not like using induction hypothesis in the previous cases. We don't, in this expression we see that we don't immediately have this. We don't see this expression here anywhere. Okay, so that in its place we can write 3k, that we don't see. We have to make this happen. We have to recognize this expression inside this product. Okay, for that purpose, let me first, since we have n here and we have n plus 1 here, so we have to separate this out. N times n plus 2 times n plus 6 plus n plus 2 times n plus 6. Okay, this is going to be somewhat large, right? Now this is equal to, now in place of n plus 2, what do we have? We have n plus 1. So here also we have to segregate n into n plus 1. Actually n plus 1 plus 1, but after multiplying I have n plus 6 plus, we have 1 here, so n times n plus 6 plus, remember this was already there, n plus 2 times n plus 6. Now here also we don't need n plus 6, we actually need n plus 5. So I can write this as n plus 5 plus 1, and after multiplying that out I have n times n plus 1 times n plus 5 plus, we have 1 here, so n times n plus 1, and this one I can simplify since both the terms have n plus 6, so I can take them common out. Inside I will have 2n plus 2, n plus 2 plus n. So plus n plus 2n plus 2 times n plus 6. Okay, now this matches with this. So in its place I can write 3k plus what do we have here now? Now we can multiply this out. N square plus n plus, if we carefully multiply, we have 2n times n, 2n square plus, let me show the steps, 2n times 6 is 12n plus 2 times n is 2n, finally plus 2 times 6 is 12. Now you see what this becomes, 3k, n square plus 2n square is 3n square plus, how many n do we have? 2n plus n, 3n, 3n plus 12n is 15n plus, and we have 12. So the final expression that we have, let me write it here. Okay. From the final expression, you can see that all the terms are divisible by 3. So if I take 3 common out, then I have k plus n square plus 5n plus 4. Now, because n is a positive integer and k is also a positive integer, this is a positive integer. So you see that this expression is also 3 times a positive integer. That's why this is also divisible by 3. So this is somewhat more complicated than the other problems, because we don't immediately have this expression for using the induction hypothesis, but we can create the expression out of the things we have in the induction steps. So this shows that this is true for all n. So you see a very nice result here from number theory, although it's a simple result. You multiply n by the next number and then you multiply that one by n plus 5. Whatever n is, that is always divisible by 3. And this result can be proved without using induction but using something else called Euclidean algorithm or division algorithm, that we will come across when we study number theory. Okay. Now to finish this application of induction, let us take one more such result and try to prove it. This one, however, will be slightly more complicated than this one. Okay. Show that 27 divides 41 to the power n minus 14 to the power n for all positive integers n. Okay. Now for this one, the beginning is the same. You take n equal to 1. What is 41 minus 14? It is nothing but 27. So 27 of course divides 27. So the basis is there for us. Next we assume that 27 divides this for some n, which means 41 to the power n minus 14 to the power n is 27k for some k in the set of all positive integers. We then have to show that this is also divisible by 27. So we work with this one. Here also we see that we don't immediately have this expression, but we can write it as 41 times 41 to the power n minus 14 times 14 to the power n. Okay. So although we don't have this minus this, but from here we do have an expression for 41 to the power n, which is 14 to the power n plus 27k. This we can use here. 41 and and we can write 14 to the power n plus 27k minus 14 times 14 to the power n. So this gives us 41 times 14 to the power n plus 41 times 27 times k minus 14 times 14 to the power n. Okay. So if we continue from here, you see these two terms, this one and this one, we have 14 to the power n in both the terms. So we can take them common out and we have 41 minus 14 times 14 to the power n plus 41 times 27 times k, and 41 minus 14 is 27. Now we can take 27 common out and we are left with this. Now this is a positive integer, so we have expressed this difference as a positive integer multiple of 27. This simply means that 27 divides this difference also. So this is our induction step. It's complete and the induction proof is complete. So here also we have got a rather strange and nice result that whatever be the value of n, whatever positive integer n may be, however large, you may have 41 to the power 100 minus 14 to the power 100. This will be an extremely large integer, although we have 41 to the power 100, 14 to the power 100 being subtracted from this one, but since this is quite large and this is also large but not as large as this one, so the difference will stay large. We don't really know what the difference is, but we at least know that it is divisible by 27. Okay. Yeah. So with this we conclude the application of mathematical induction, and we have got a nice practice in writing the solutions that require mathematical induction. Okay.